What I'm going to ask, did anyone think about the witness table construction algorithm, the linear time construction algorithm for the witness table? And okay, there are two parts to the question. Part one, did anyone think about it? Part two, did anyone successfully think about it? Yes. Yes, go ahead. Okay. I think also if you can explain to the audience. Maybe I will even give you the. No? Okay. 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 Yes, unless you get stuck before, if it's already not the same. Yes. Hmm. Yes, that's an O of one time. Okay, so let me see if I understand. Um, so you're saying you have you have this, and it goes all the way to here. Fine. You have I. This is I. You have I. It goes all the way to here, um, and that's where the error is. If it goes all the way to here, it means that this is the beginning. Okay. Now you're saying about I plus one. So what do you know about I plus one now? So how do you know that this is the same? This is so. This is the beginning. You're saying, right?
if
but
I take these two, this is actually witness 2. If I take witness 2, I get the inconsistency.
so what you're saying, between them you
Yeah.
have witness 2,
Yeah,
and witness 2 is here,
is here.
is
These
here.
are different. So
Okay.
then, and I'm saying this is the nearest inconsistency. So then this string till here is equal to this string here.
Hmm.
And then I compare these two, and I'm saying this is the nearest inconsistency. I know for I don't know of these two, but I know this two. So this is the nearest. So again, this string is same as this string, the one before these. So n by transitivity, because I know this is, so then this part is equal to this part. So and also this, whatever the symbol here was, it will be here because this was the nearest inconsistency. And this symbol is not equal to this, but this is equal to this. So these two are not equal.
So this would be the inconsistency here.
Yeah, so these two.
Yes, for wi plus 1
Yeah.
is going to be this.
And I claim this is the nearest one because this string is equal to this string.
Okay, so this is in case. So that's the case where these two,
Yeah,
where this is smaller than this, and this is the case where it's bigger.
yeah.
And in the case where it's bigger, you're saying that again.
The nearest
So
one is this, and here it's this. So then again,
so wait. What you're saying is W2 is here. W2 was here, and the WI was here. And now what you're saying is that WI is here and W2 is here?
yeah.
Okay. So if WI is here, um, then
First we compare these. This string is
yes.
the same as this. And again, with these two, this string is this
And
block
yes,
is
and
the
because
same.
this
And
one
this
is further, this is
transitive.
the error. Okay. Okay, so what we see here, did people understand what she was explaining? This was not the way that I thought about it, which is nice. But it seems to work. So did you manage to understand the explanation, or should I try to go over it again? Shall I go over it again? Yes? Okay. All right, so what's your name again? Yes. Okay. So Forum explains the following. She says, what we want to do, so we have a witness table, and we want to fill it. So we want to fill the witness table, and we want in general that the overall time to fill it is going to be O of m. In other words, we cannot afford to actually look at every shift and compute the witness table for that shift. So what she's saying is the following. Let's assume that we computed, so W1 of course is a star, and let's assume that we computed W2. So this one is filled. And now then, so for that it's still O of m, of course, because you do one of them, it's not a problem. Now let's also assume that we are now in position I, and assume also that we computed Wi. Now, the idea is the following. If we compute Wi, and we do that in a brute force way, in other words, we compare, we put the shift here. We shift the pattern, and we compare in order to compute the Wi. And at some point, we reach a location that's not right. That's an error. Now the idea is we want to try to fill all the positions between wi and the place where we were stuck. We want to fill those positions in O of 1 time without actually needing to recompute the shift for every one of them. Because if we manage to do it that way, then at that point we get to the error, and then again we do the same process. So this would be the new I, and we will continue from there up until we get stuck, and we fill all the elements in between in time O of 1, and so on and so forth. So the overall time, if that is what you're going to do, the overall time is going to be the O of n, O of m, because you did the every time you do an I until you get stuck, and then you continue another I, and you get stuck, and continue another I until you get stuck. So you add up all of these, you get m, and then you have another O of m in order to fill in all the elements in between until the place where the ith position got stuck. And if we fill those in time O of 1 each, then we've used another O of this segment. So this segment we did twice, and then the next segment we're going to do twice, and the next segment we're going to do twice. So far, this is what you're trying to say, right? Correct. Okay, so now so that's the general idea, and the only thing now left to do is to show how do we actually fill the elements in between if we know what is the how far the wi continues. Okay, so now this seems to me Foram's key observation. She says, if you look at I plus 1, okay, I'm trying to fill in I plus 1. If you look at I plus 1, then what do you know about it? The difference between I and I plus 1 is really the difference between 1 and 2. Because if I up until here is actually equal, if this is where we have the error, it means that from here to here, I is actually equal to the beginning. So this is the beginning of the pattern. So that we know. Now, if that's the beginning of the pattern, and when we go to, so when we're asking about the difference between I and I plus 1, since this is equal to the beginning of the pattern, then in fact, the difference between I and I plus 1 up until here is like the difference between 1 and 2, because this is equal to everything from 1. Okay, so now there are two cases to consider. What do we know about the difference between 1 and 2? Suppose that the difference between 1 and 2 is actually smaller than this distance. In other words, so this is 1, and if 2 starts here, already W2 would be somewhere here. So this would be the W2. Now, if we know that, then what can we say about I plus 1? Well, since I plus 1 actually extends the beginning all the way to here, that's what I plus 1 does. Sorry, I extends all the way here from the beginning, and I plus 1 is equal to the beginning here and here, but this was already a witness in W2. This was an error. In other words, it has to be an error for I plus 1, because I plus 1 cannot extend anymore. Since we know already from here that if you start from the beginning and you put something under and you try to shift, that's not going to be equal in this location. So the fact is that here, this is equal to the beginning. So if we want to if we ask ourselves, the second position from the beginning where we get stuck, it's going to be here. So therefore, you know already in time O of 1 how to fill in I plus 1, because basically you just take what W2 wrote and shift it appropriately. Add I to it in order to uh, to show where the error is. But that has to be different. So that's the case where the where W2 is actually smaller than Wi. Another case that one needs to consider is what happens if W2 is longer than Wi. So, okay, so this case is clear to everyone? So in fact, the time that you spent to fill Wi is O of 1 in case W2 is smaller than Wi. Or the offset, when I say is smaller, obviously we mean the offset because you need to always add the appropriate beginning, the appropriate I, since 1 and 2 start at 1 and 2, and this start at I and I plus 1. So you will need to add I to what you get here. But that's a single arithmetic check. You check whether this is less than that, and if it is, that's what you put in there. So in time O of 1, you filled in Wi plus 1. Now, the second case is when, in fact, W2 extends longer. So Wi is the same up to here, but W2 would have gone on longer, would have gone on to here, let's say. So what can you conclude from that? So at this point, I'm asking the question because you should have the idea here. Exactly. So this is going to be the Wi plus 1 because W2 says that if this was actually equal to the beginning, then I plus 1 would have gone on all the way to here. So it means that whatever was here in the beginning is what W2 wants to see there. Is what W2 sees there, not wants to see there. But we know that that's not what's here because already Wi says this is my witness. So what is there is not what is in 1. But W2 says it is. So therefore, Wi plus 1 says this is going to be my error. So again, in time O of 1, we can we managed to figure it out. So this is how we fill Wi plus 1. Now, the only thing that we now have to figure out with this idea is what happens now with I plus 2. So because we really need to fill up everyone all the way up to here. So in the case where the distance between W2, I think you're going to need a similar kind of argument for W3, W4, W5, because W2 is going to be good for I plus 1, but you'll need W3 because you really want to fill everybody up to here in order to be able to continue in a linear progression. So it's okay, you do have W1 to Wi. You have all these, you filled all of them, and you think that and I think that you're going to need to use all of them in order to figure every one of the. Yes, but already then you need to be careful about your limits, because how far does Wi plus 1 extend? If Wi plus 1 only extended up to here, then if Wi plus 1, because Wi went all the way here, good. But if Wi plus 1 only went up to here, at this point, you're going to get stuck here and you don't have information anymore. So you will need further W's. So in case the W2 goes all the way, you're right, you have all that information. But in the shorter case, where the W1 is smaller, then at some point you're going to need to look at other elements. So, but it's okay. So the idea, I think, I mean, I'm glad you showed it because this is not at all the way that I thought about it. Um, but the idea that then would be when you're looking at I plus 2, you do the same thing, but you look at the W3. And you do the same argument as you did for the W2 for the W3. In other words, to fill the W3, you also need to just check the relation of where W3 is as opposed to WI plus 1. And you do all of them until the end of the WI plus 1. At that point, you start again. That will be your new WI, and you continue. Okay, so I think that that would work. Thank you very much. So we can now continue. Ooh. And it's an alternative to Knuth, Morris, and Pratt because it's also a linear time algorithm. And we just showed that we can construct the witness table in linear time. And then we have the duels, which are done in time O of n. And then the verification, that's the wave, and that's also O of n. So we matched everything, and it's alphabet independent. And that was all good for one dimension. Now, when we're going to two-dimensional matching, so it didn't come up yet. Okay. In a number of places, so you'll see that it's here and here. It doesn't occur here because the C is not equal to the B, and it doesn't appear here because this B is not an A. So maybe I can also now turn off these lights. Okay. All the positions in the two-dimensional text, we want to make a dual between them and make sure that only a small number of candidates are left. And this small number of candidates left, we're going to then, okay, so our dueling mechanism is going to be such that the candidates that are left agree on the overlap. At that point, we'll be in exactly the same position that we were in one dimension. We'll be in the position where every location in the text is either good or bad. We're going to check if it's good or bad. And then we're going to drown all those that have within their m by m range a bad position. So that's the idea, and it seems like an excellent idea, but now we need to see the implementation because ideas are good, implementations are more of a problem. So what I think I didn't tell you last time was that the idea of actually using Yayo and Korasik to find the rows and then KMP to find the column appeared in 1976 and in 1977 independently by two researchers, Bird and Baker. So it's called the Bird and Baker algorithm. It was exactly the same algorithm, but it went through the reviewing process in different journals and different reviewers. So it was accepted to two journals by two different people, same algorithm. So it was published twice. That's not such a horrible thing. And twice is even not that big a number. The famous dynamic programming algorithm for edit distance that you may have seen in some of your classes actually appeared over 13 times in different journals in different fields because biologists came up with it and computer scientists and various different people in different fields. So Tzvika Galil actually counted it once and he came up to 13 and he thinks that there are more that he couldn't find. So just two is not so bad. So the Bird and Baker algorithm is this one. Now, the Bird and Baker algorithm, as we saw, the time is really O of n squared, log of the alphabet. And if the alphabet is infinite, it comes out to n squared log n. So the question was, can we find an algorithm that is independent of the alphabet size? So you don't have the log of the alphabet like this algorithm does. And so the algorithm, the witness table algorithm, or the dual algorithm that I showed you, appeared in '91, and that was a paper by by me and Gary Benson and Martin Farage, who were both my PhD students at the time. Today, Martin is a professor at Rutgers and Gary is a professor at Boston University. So, but in 91, they were still both PhD students. So that was that algorithm. And by the way, yesterday I got happy news that my 21st PhD student's dissertation was approved. So, and I have 2 in the pipeline now, so we'll see what happens. Um, okay, so what we want to do, is a witness table algorithm, but in 2 dimensions. So in other words, suppose we have one candidate here that says this is where the pattern starts, and we have one candidate here that says this is where the pattern starts. We want to be able to kill one of them by a duel in time O of 1. And we should be able to do that by the same idea as we saw before, if in this area of the overlap where they intersect, if there is a difference between what the leftmost guy, the top left guy wants to see, as opposed to the bottom right, if there is a different symbol, this one wants to see here A and he wants to see here B, let's say, at that point we can say this IJ is actually a witness that will enable us to kill one of them. So we're going to have exactly the same dueling algorithm as we had before, except it's a 2-dimensional duel. So if our witness table is going to be 2-dimensional, and so if in this area, if in KL of the witness table, what we're going to put here is IJ, where IJ is the index of the discrepancy in the overlap. The problem is that it's not enough. Why isn't it enough? Because we're talking in 2 dimensions. So consider this. If our witness table in position KL has an IJ, where IJ means that if I take the text and in KL I take the pattern, and in KL I put the pattern again, then in I and J, this particular guy wants to see an A, and this guy wants to see a B. So in other words, there's an A here, and the B here, or a B here. But when you overlay them one on top of the other in position KL, that would be the discrepancy, so we put IJ. And the dual is going to allow us to kill it. But what are we going to do about this kind of situation, where this is 1 and this is 2? Where is it going to be in the witness table? Okay, so in 1 dimension, when you have just a string, you shift it, you can only shift it one way. But in 2 dimensions, you have more degrees of freedom. And it doesn't, you don't only shift things this way. You can take the pattern and you can pull it this way, you can pull it that way, you can pull it down this way, and you can pull it down that way. So you really can pull it in 4 ways. But the 4 isn't 4, it's only 2, because it's symmetric. I mean, going down this way is the same as going up this way. So we don't really have 4 directions, we have 2. So we have this direction, going down that way. But we do have another kind of direction going up this way or going down this way, which is the same. And that's a different direction. So we can't anymore assume that we have a witness table that answers all cases. So I'm going to give you the solution, but I want to make sure everyone sees the problem. Okay? It's the dimensional problem. You can move things in more ways than one, whereas in a string can only move to the right and left, but in 2 dimensions you can move in more ways. So the way that we solve it is going to be by having 2 witness tables. One witness table that goes this way to the right or southeast, as they say, and another one that goes northeast. So you have the northeast witness table and the southeast witness table. So you have 2 witness tables. And so what we're going to do is do a bunch of duels and make sure that at the end of all of these duels, everyone agrees in the southeast direction. But it could be that in the northeast, not everyone agrees. So then we take the remaining people and we do again a set of duels, but now using the northeast witness table in order to kill out all those that are incompatible. And at the end of both of these processes, we're going to have everyone compatible in all directions. What does it mean? You still have O of, it's still linear. You have O of n squared, but it's 2 times the, you're going to have to do it twice. So twice is still big O. So, but what it means is that if you want to then take this algorithm and extend it to 3 dimensions and 4 dimensions and 5 dimensions, you can do all of that. But every dimension that you add is going to add a witness table because of another direction. If you look at a cube can move this way, that way, but also this way. So it has already 3 dimensions to move at. And if you look at 4 dimensions, which I can't even wave my hands and show you anymore, but then you would have 4 witness tables. So this algorithm is going to be alphabet independent, but it is dimension dependent in the sense that it's going to be O of D times the size of the input, where D is the number of dimensions. In what? Yes. Yes, yes, yes. It's like because, okay, so in 3 dimensions it's easy to see. So if you take this in 3 dimensions, then you can move in that, in each one of these directions, you can move it that way, you can move it that way, and you can move it this way. So every coordinate, so notice, because in some sense, we don't have okay, so for 1 dimension, you can shift things to the right and the left, but because of the symmetry, your witness table is only 1. You don't need 2 because it's the same. You have the left and the right. In 2 dimensions, you can shift it also in 4 ways, but you fix the east, let's say, and so then you have northeast and southeast. In each one of them, you're going to fix the dimension and then you move the others. So the direction and then you move the others. So it's going to be D. Now, the truth is that if you want to use AO and Korasic or KMP for bigger dimensions, for higher dimensions, you're still going to get the dimension. So you're not losing anything. I mean, look what we did with AO and Korasic. You had O of n for 1 dimension, and then you had O of n for the KMP on the columns for the other dimension. So whenever you're going to do dimensions, the dimensions are there. The idea in this algorithm is that you get rid of the dependency on the alphabet. So the alphabet, no matter what it is, you're still always going to be linear times the number of dimensions. Now we're going to do it in 2 dimensions, everything generalizes. So, so in fact, we said everything generalizes, but a couple of years later, someone published an article saying, oh, we can do it in 3 dimensions by showing how it generalizes. I said, well, that person can actually now have an infinite number of papers by showing how to do it in 4 dimensions, in 5 dimensions, in 6. But it's the same concept. So I'm only going to show you 2 dimensions. So we're going to construct 2 witness tables, as you see here. One of them, where the ij is going to, in location ij, it's going to give the coordinates of the error in the overlap in this direction. And in the other one, in ij, you're going to get the coordinates of the overlap in that direction. Now, let me also say something else. From now on, I'm not going to actually show you both of them. I will show only one. And I will show how to deal with this witness table. But what the important thing to remember is that if I show you only this, that's quite fine, because this witness table, you don't even need to think too hard about how you deal with this one as opposed to this one, because if you take this witness table, now you're going to do a little bit of geometric projections in your mind. So if you take this and just move it, rotate it 90 degrees, what you're going to have is this situation, right? So if you rotate it 90 degrees, it's this situation, which means that if you really only want one algorithm that deals with your dueling, and the algorithm that deals with it is the one that I'm going to show you, so to run it for the other one, just rotate the pattern in the text by 90 degrees and run the same algorithm again. And that's going to solve the other case. So easy. But this needs to be said, because from now on I'm going to ignore the second witness table and only deal with the first one. But what you should have in mind is that we really have 2 witness tables. We're going to duel with 1 witness table. And at the end of that duel, we're going to prove that everyone that is left is going to agree in the overlap when the overlap is southeast. And then you're going to need to run it again and duel. And you now don't need to duel with everybody. You just need to duel with the remaining ones, those who stayed up from here, because everybody else is already dead. Whoever is dead is dead. So you only duel the remaining ones, and you kill off all those that you can kill off because of the second witness table. Then you're going to end up with a number of potential candidates. These potential candidates are the ones that you have to verify. So you're going to need to run through these potential candidates, find out for every text location what pattern, what pattern coordinates everyone wants to see in that location, write the good and the bad, and then do the wave back and kill all those that don't match. Same algorithm as we did before, which is why I started out by the 1 dimension, even though in 1 dimension it's not a complexity new result. But I think that it aids in the understanding. So in fact, the 1-dimensional algorithm never appeared anywhere because it was not interesting as a 1-dimensional algorithm, only as a pedagogical aid. So the algorithm is the same. We eliminate the conflicting sources, and then we verify. The question now is, how do we do the dueling stage? Because it now is a 2-dimensional duel. So how do we do it? So this picture tells it all. And I'm going to do this a lot faster than I did the first one. And it's a little busy, but since now you already know so much about the 1 dimension, so everything else can go faster. So what we do is the following. The first thing that we do is we go through all the columns and we run the 1-dimensional dueling algorithm that we did before in order to make sure that within a column there are no conflicts. Now, the algorithm is exactly the same algorithm that I showed you yesterday with the animations, except it's in the column rather than in a row, but it's in a column. And the only difference is that when I say duel between this location and this location, what I mean is do a two-dimensional duel. In other words, go to your two-dimensional witness table and kill off whoever needs to be killed off, even if the error in the overlap is not within the column. Okay, so in one dimension, we would just look at errors within the column, but now we're doing two dimensions. So you go through, you do the same algorithm, exactly the same algorithm, but when it says dual, go to the two-dimensional dual. So a candidate can be killed if it overlaps the other one somewhere, even not in his own column. But so far, it's exactly the same thing as we've done before. And the situation at this point is that we have, in all the columns, the candidates don't conflict within a column, but of course, different candidates in different columns may conflict because we didn't dual them. So now we need some method to dual candidates in different columns. Okay, so what we're going to do, and the way that this algorithm is going to work, it's going to go from right to left and from the bottom to the top. So the first column that is actually a reasonable column is going to be the n minus m plus 1 column, because everywhere else there's nothing, and here we checked. So this column is now completely okay. So if we're going from right to left, and our induction is going to be that as we move in the columns, we make sure that everything to the right of where we are is okay. Well, when you're looking at the very first column, that's reasonable, then we know that everything is okay. So that's the beginning of our induction. So we know that the first column is fine because we ran that algorithm. So now we go to the next column after that, and the next column after that, and the next column after that, and from the bottom to the top, we make sure that everything is okay. So let's assume that we have reached all the way here, from left to right, all the way here, and from the bottom all the way to here. So all of these candidates that you see here, 0, 1, 2, 3, 4, 5, all the circle ones are those that are left, and our inductive hypothesis is that they all agree with each other in the southeast direction. So these two may not agree, but these two agree, and these agree, and these agree. Okay, because we're only using the first witness table at the moment. All right, so that's our assumption. All of these guys agree in the southeast direction. All of the guys up to here all agree within the column, but we now need to make sure that all of these people agree with everybody else. And we need to do this without actually dueling everyone against everyone, because if we do that, it's not going to be linear. All right. So let's start with 8, 9, 10, with 8, 9, and 10. Okay, so our inductive hypothesis is that all of these agree. And we know also that 1 and 7 agree because they're in the same column. Okay, so this is what we know. We know that 1 and 7 agree. We know that all of these guys agree. But now we are asking 1 about 1 and all of these other people. Who does he agree with? And who not? Because if he conflicts with one of them, then somebody is going to die in the duel. So let me start by asking, do I need to duel 1 and 7? I know I don't, because they're in the same column. But what about 1 and 8, 1 and 9, and 1 and 10? Do I need to make a duel between them, or can I assume that everything's good and just ignore them? The answer is we can ignore. Why can we ignore? The big T, because of transitivity. Now, our inductive hypothesis says that 7 and 8 and 9 and 10 agree. And it also says that 1 agrees with 7. So now this calls for a little drawing. So if we look at the pattern, let's make it all encompassing. So if we look, let's say that this is the pattern, and this is the pattern, and this is the pattern, and this is the pattern, okay? So these are all the occurrences of the pattern, and they all agree with each other. So let's concentrate on the 8. So 8 and 7 agree, which means that everything here is the same. Now, 1 and 7 also agree. So this is 1 and 7. The overlap of 1 and 8 is included in the overlap of 7 and 8. And so therefore, we know that 1 has to agree with everything here, because 1 agrees with 7 for this entire area, 7 agrees with 8 for this area. So the intersection of 1 and 8 is within that. So by transitivity, 1 and 8 agree. And the same thing holds true for everyone southeast of 7. Maybe I can even leave it like this. So one doesn't need to worry about 8, 9, and 10. So the first dual that we're going to do is between 1 and 4. 1 and 4 are going to do a dual. Now, what can happen? 4 may die. If 4 dies, we take him out. 1 may die, and if 1 dies, we take him out. And we're going to move on to the 2. In each case, if you remember our famous observation from yesterday, that the dead person pays for the duel, and nobody duels twice, so there's only going to be a linear number of duels where someone dies. So if 4 dies, we take him out, and then 1 is going to duel 5, and then if 5 dies, we take him out, and 1 is dueling with 6, etc., etc. But it doesn't matter, because as long as they die, we'll duel again and again and again and again. The dead person pays, and we're still linear. If 1 dies, we go on to 2. So again, the 1 pays. But what we need to worry about is always the case where there's no one dies. There was a star. So let's say that 1 and 4 were good. There was a star. No one dies. Well, what can we say then? Does 1 need to duel with 5 and 6? No. If 1 and 4 are okay, then 1 doesn't need to duel with 5 and 6 because of the very same observation of the transitivity. Because 1 is here and 4 is here, and they're okay, and 5 is in the same row, but is a little bit shifted, and 5 is here. So 4 and 5 are equal because of the inductive hypothesis. 1 and 4 are equal because of the dual. Therefore, 1 and 5, which is this area, is going to have to be equal because of transitivity. Okay. So if we duel 1 and 4 and no one dies, we do not need to duel anymore on the row, and we go on to the next row because I don't know anything about 1 and 3. So I'm going to be doing another duel between 1 and 3. And then I'm going to duel between, if one of them dies, good, and if not, uh, then I finish with the row and I go up to the top row. So what's the conclusion when we're talking about time here? How many duels are we doing? There are going to be duels where people die. And those we already said we don't worry about because there's a linear number of such duels. As far as the duels where everybody stays, where we add a star, we only have one such duel per row. Now that may seem to be concerning because it means that 1 actually does a bunch of duels before moving up to 2. I mean, the reason that the stars were linear in the 1 dimension is because every time that we dueled, we moved over. And here we're not moving, we're dueling more. However, this is where the initial stage came in because we're not really, we already in linear time um, sparsified the column. So we don't have everyone. So 7, 1, and 2 are far from each other because we already killed all the guys who didn't agree with them. So in fact, ask yourself, how many duels does 1 do in the worst case? Well, he's going to duel every row, and then he's going to stop. And then 2 is going to duel every row and stop. So the number of duels that are that have a star is actually equal to the length of the column, because every element in the column is going to the number of duels it's going to do is between him and the next, and then the next is going to do the number of duels where there's a star between him and the next, and him and the next. So if you add them all up, you're going to get n. So for every column, we only have at most O of n duels where there's a star. Since there are n columns, so we get O of n squared duels where there's a star at the worst, but that's linear. So this is the dueling algorithm for 2 dimensions. The time, as we saw, was linear. And as far as the correctness, well, we actually worked it out according to the induction. So every time that we moved on, the next person agrees with everyone in his southeast because of the transitivity. So the algorithm is correct, and the algorithm is linear, and the algorithm is 2-dimensional, but there is no dependency on the alphabet. Because where is the alphabet? You just duel. And a duel means you go to a location, you open it up, and you either kill this or that. The duel is O of 1. There is no alphabet dependency in this algorithm. Okay, so the total time, as we said, is n successes per column, and there are no more than n squared fails total, where fails is where someone dies. So altogether, we have an O of n squared algorithm. Now, we're going to do a similar O of n squared sweep for the, you can't read this because the, okay. So you do a similar O of n squared sweep for the other witness table. And at this point, we've spent O of n squared time, and we have a beautiful grid where all the remaining candidates agree with each other. So we need to verify. And what we're going to do here is the wave. And in fact, the wave as I told you, the wave was invented for the 2 dimensions and not for the one, because in the 1 dimension you can actually kind of do it without the wave by formula. But, but in 2 dimensions, it got to be very complex. So here, let me rotate this and draw on it. Okay, make it smaller. How do I get it up? Since it's the end of the, so it's a, yes, that's true. We can resize the window. Yes, move the window up. Good idea. Maybe a little bit more because I want to draw on it. Yes, excellent. So here now is the 2 dimensional wave in all its glory. The, um, the, the candidates are here. These are those who remained alive, and it means that they agree on all the overlaps in all directions because they all survived the duels. It's a 5x5 pattern, so it means that uh, these green squares are actually the occurrences of each one of the patterns. So our task is to find out for each element here in the text what uh, what does he want to see there, because whatever needs to be there is going to be either good for everyone or bad for everyone. So we want to see what does everyone want to see in each location. So we can start by doing a horizontal wave by the rows. So he starts a wave and he goes 1 2 1 3 1 4 1 5, and the wave finishes because there's no one else after that, and 5 is the length of the wave. So now we start the second wave. 1 1 1 2 1 3 1 4 1 5. Then we go with the next wave. 1 2 1 3 1 4 1 5. And in each one of these the wave finishes. Now notice that the wave finished over here, and there are still elements that we need to know what they are, but we don't know it because of the horizontal wave. Here we have 1 1 1 2 1 3 1 4 1 5. And that's the end of this wave. Here we have 1 2 1 3 1 4 1 5, and we finished all the horizontal waves. But at this point, now we're going to fill out everything else. So we're going to do now the vertical waves. And every vertical wave is going to start in when it has a number, and it's going to continue. And as the nature of a wave is, if in its direction it needs to start again, it's going to get recharged and start again. So for example, here, it starts with 1 1. It wants to see 2 1 here, and it wants to see 3 1. And then he says to this guy, well, yell 4 1, because that's what my candidate wants to see. But he says, no, 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 no. I have my own number. So I'm going to yell 1 1. And then it's going to be 2 1, 3 1, 4 1, 5 1. So we finish this vertical wave. So now we go to this 1 2. So 1 2, 2 2, 3 2, and he says to him 4 2, because what I want to see here is 4 2. But again, he says, no, I already have a start. So I have a 1. So it's a 1 2, 2 2, 3 2, 4 2, 5 2. And then we go on this column. So 2 3, 3 3, and then we start again. So 2 3, 3 3, 4 3, 5 3. And then this guy, 1, 4, 2, 4. But there's a 1, 1 again. And he goes down. He says to him, say 2, 1. He says, no, I already have a number. And then he goes down again, 1, 1. Good. So say 2, 1. So that's what he says. 2, 1, 2, 3, 1, 4, 1, 5, 1. Now, notice what happened here. These guys are filled up to here, and we didn't continue. The reason we didn't continue is because this 1, 1 actually is going to go further. So we don't want to continue here. We're giving him the precedent. And he goes down further. But the point is that by filling all the horizontal ones and then going down vertically, you're always going to ensure that you can continue with the indices as far as possible in this direction. So again, 1, 5, 2, 5. Full, full, full. 2, 2, 3, 2, 4, 2, 5, 2. Now, the beautiful thing in this here is that when you have an index, at this point you don't even know why you have that index. But you know that that index is good for some potential candidate. And you know that all the potential candidates agree. So you know, fine, if I have an index here, it's good for whoever is here in these indices. The whole idea of the wave is only so that you'll be able to fill all the locations that are relevant. So what the wave does is exactly that. It enables you to extend to the maximum, both horizontally and vertically. And so you fill out everyone. So let's just do it because we're close to the end. 1, 1, 1, 3, 2, 3. 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 1, 2, 1, 4, 2, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, and then 1, 3, 1, 5, 2, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, and the last of them. 2, 3, 4, 4, 5, 4, and 2, 5, 3, 5, 4, 5, and 5, 5. So as you can see, every single element in the green rectangles is filled, which means that this is pattern 1.2 is what everybody wants to see here. Pattern 1.4 is what everybody wants to see here. It's true that he wants to see 2, 2, 4, and he wants to see 1, 4, but it doesn't matter. The dueling stage says they're the same. Okay, so we did these waves. That's totally linear. In fact, well, it's 2 times n squared, one for the vertical, and one for the horizontal, and one for the vertical wave. So we ran these waves, and we go through the text now, and we do the comparisons. And every time we compare, what we need to do is compare this element in the text to 2, 4, and we write yes or no, depending on whether it's equal or not equal. So at the end of this process, we have a text with yes and no's. And every element that has a no in its range of m by m is bad, is not an occurrence of the pattern. So we now do the wave backwards. And the wave backwards is going to be the horizontal wave and the vertical wave backwards. And so any person who is caught within this, or any potential candidate that is caught within these waves is going to drown, and there is no occurrence. So at the end of all of this, all of these waves that are running all over the place, which is all linear, whoever is left standing is an occurrence of the pattern in 2 dimensions. Okay, so that is the end of the ABF algorithm, alphabet independent 2-dimensional matching. Any questions on this? Anything still not 100%? Yes. So the one thing that I always tell you at the end of this is to construct a witness table in linear time. Well, constructing a 2-dimensional witness table in linear time is not a simple thing. And in fact, in the original paper, the construction was not linear, and it used very powerful techniques which you don't have yet. We're going to see them later in the course. But the time was still m squared log n, log m. Now, m squared log m, of course, is a lot, since it's a lot better than n squared log m. And so, and usually for m's that are not too big, it's going to be smaller than n squared anyway. So therefore, that paper was a Fox paper and SciComp, et cetera, even if the witness table construction wasn't linear. After that, we actually worked pretty hard and we figured out a linear witness table construction. However, we were scooped by a stock paper of Galil and Park, who did the linear time two-dimensional witness table construction just a couple of months before us. So I'm not leaving that as an exercise for you to come up with a two-dimensional linear time witness table construction. It's actually not easy, but exists. The construction of? The trivial construction is m squared. You can always do it in m squared. The m to the fourth, yes. So you can always do it in m to the fourth. What we did it was in m squared log m, using suffix trees and LCAs and all kinds of things that we're going to see. But could be. I didn't think because we tried to get it as, so it could be, I don't know. So that can be an exercise if somebody wants to think of an easy m cubed construct for the witness table. Okay. So now that we're done with that, so what have we seen? We have seen an algorithm this is supposed to stop the projector. Whatever. Double press, okay. Pratt algorithm. And if you look at the witness table algorithm, all of them, both of them anyway, these are the ones that we know, are extremely serial in nature. You're going one by one and you're going back, and or you're waving here and waving there. How do you do these things in parallel? You basically need to know where you were in order to know what's the next step to take. So you need another kind of idea in order to do even the regular string matching. And so again, I'm going to show you the serial algorithm, but with a different concept, a concept that's local. In other words, that is not serial in nature, in order to be able to utilize parallel architecture if that's what we have. Now, in the 80s, there was a very popular parallel architecture called the PRAM, that a lot of parallel algorithms were written by that architecture. So the PRAM architecture said the following. Now, the RAM is the random access machine. That's the architecture that we do our serial algorithms with, and the von Neumann architecture. But it basically says that you have your central processing unit, you have your memory, and the CPU accesses the memory and does the logical works and reads and writes to memory. So that's the random access machine. And it's random access in the fact that we assume that it takes O of one time in order to read and write from any place in memory because in a Turing machine, for example, you can't assume it. So in order to get somewhere, you need to maybe sometimes run O of n time just to get the next element in memory. But in the random access memory, random access machine, you can go anywhere in the memory, and that's what most of our when we do algorithms nowadays, that's what we do it on. We don't do it on a Turing machine. So we do it on a RAM. So in the 80s, people said, okay, so if we want to do parallel algorithms and we want a general model for parallel algorithms, we want a model that is not going to be dependent on this particular architecture or that particular architecture. In the 80s, there were all kinds of parallel architectures. There was a pyramid, and there were all kinds of hardware companies that came out with parallel machines. And so each one of them had a different architecture. And you don't want to be dependent on architecture. We're going back now to the first day when we spoke about it. If we were science, we're not dependent on architecture. So we need some model that is a general model, and that is going to be a benchmark that will tell me about parallel algorithms on all architectures. So they said, well, there is a random access machine. We're going to define a parallel random access machine. So what's a parallel random access machine? It means that you have a bunch of CPUs all over the place, and you have a memory. So this is your memory, and these are your CPUs. And every CPU can random access the memory. But it's different CPUs, so they can do work in parallel. So this guy can compute something, and this guy can compute something. Each one of them can compute something. But they all have random access to the same memory. And that allows them to talk to each other, and it allows us to write a parallel process where the different parallel processors actually communicate. So this communication is done via the memory. So in time O of 1, everyone can write into the memory. In time O of 1, everyone can read from the memory. And in fact, it's not sequential, the writing and the reading, because they can all be reading from the memory at the same time. So the model is as general a model as you can do, as you can think of. So it says they can all read from the memory at the same time. They can all write to the memory at the same time. But here, we're going to stop, because we're going to say, all right, I go along with your fantasies about everybody reading from memory at the same time. Good. No harm can be done. If you can figure out some way to do it, good. And if the architecture has some delay because there's a semaphore or whatever, good. But how do you model writing together at the same time? If they write in different, memory locations, then fine. Let them all write at the same time. But what happens if a number of different processors want to write at the same location at the same time? So at that point, they came up with a number of different PRAMs. So they had the ER-EW PRAM, no, the CR-EW, CR-CW, and there was also an ER-EW, but that is less of a concern. So what's an ER? What's the R and what's the W? R is read, W is write, and the C and the E are exclusive or concurrent. So in an ER-EW PRAM, there's an exclusive read and exclusive write. In other words, they even force you to only one processor can read a particular memory location at the same time. So you have to write your program in a way that guarantees that this is done. Otherwise, you have an exception and your program flies out. It's wrong. It doesn't compile or it doesn't run. So that's an exclusive read, exclusive write. And a CREW PRAM is concurrent read, exclusive write. which means, okay, no harm is done if a bunch of people can read the same memory location, so it's a concurrent read, but it's an exclusive write. Again, the onus is on the programmer to make sure that no two processors are going to try to write simultaneously at the same time. And then there's the concurrent read, concurrent write, which is the most liberal that you can be, because you can read, you can write at the same time. But the question is, you now need to define what happens when you write into two locations, when you write into the same location with two CPUs. By the way, notice that there isn't an ERCW, because that doesn't really make any sense. If you're going to exclusive read, then why are you concurrent write? I mean, why? Reading somehow seems easier. So these are the three models that appear in the literature. Although from a combinatorial point of view, there is also a ERCW, but it doesn't make sense. So nobody ever wrote an algorithm for an ERCW. So these are our models. And as I said, for a CRCW, we need to figure it out. So here there were submodels in the CRCW. Yes. For the exclusive read, people said that, you know, in a real architecture, we don't see how it can happen, because you're going to go to some place and get it. How can you do it at the same time? So they said, so you may as well write an algorithm that doesn't allow this, so that you for sure know that it works everywhere. And the motivation for this is to say, look, what I want to do is a benchmark. I want to see what is the fastest I can do in parallel, assuming that nothing stands in my way. If you think about it, the random access machine is also making assumptions that physically are not exactly right. And we know that we're making these assumptions, because okay, so in data structures, you probably all studied about red-black trees, or 2-3 trees, or AVL trees, or anyway, binary sorted binary trees, dynamic sorting trees of various types. And then you also learned about B trees. But B trees, what's the idea of B trees? It's the idea that what happens if you have a disk. So a disk doesn't behave the same way as a memory. And in fact, a memory doesn't behave the same way as a cache. So you have a hierarchy. So you have a cache, you have your registers. Anything that you can do within the registers is really super, super fast. And then you have your cache memory, which is a few megs, and at best. And you can do things very, very fast. And then you have your memory itself, which is a few gigs, and you can do things pretty fast. And then you have your disk, and you can do things a bit slower. And then you have even slower if you really are talking about huge petabyte storages, they're even slower. So when you write an algorithm, it's not true that you have a random access machine. It's not O of one time to access every location. But even in the memory, it's not O of one time to access every location, because where's the electrical engineer? He's not here today, right? Okay. So he would tell you that electricity actually does not go in O of one time. The flow of electricity, in fact, has a quadratic degradation. It's just that it's very, very fast, and we don't really feel it. But from a theoretical point of view, we're not really doing things in O of one time. But the model says, okay, do it in O of one time, you live with it. You get some sort of at least you can prove things. So the same thing here. The CRCW people said, okay, it may be that this is physically impossible, but I want to do a model like that, because it will allow me to investigate the limits of parallelism without getting into such nasty things like physics. So let's see, parallelism, pure parallelism, where can it get me? So that was the idea. But what they did need to do is to conceptually say, well, fine, but what happens when two processors want to write something into a location and it's not the same thing? Then what gets written? So there are three models. One of them is called the priority model. So as you can see, like I told you, like everything in the army, it's divided into three parts. So we have three of these, and now there's three CRCWs. Life is thirds. So, well, in Judaism, every number also has its meaning. So I'm sure you probably also have different numbers have different meanings, but in Judaism, numbers even have the numbers coincide with the spheres, and the spheres coincide with values. So the value of the number three is actually the value of uh, reproduction, fruitfulness, children, education. I mean, this is so everything splits into three. That's good. All right, so CRCW, there's the priority PRAM, CRCW. And the way that that works is the technology assumes some sort of a priority. Either the largest of the numbers that want to get written is the one that gets written, or every processor has a priority and the processor with the highest priority is the one who gets written. But you assume some sort of a priority, and that is what gets written when there's a conflict of what different algorithms, uh, different processors want to write. Then there's the random, and random says, look, I don't know. A bunch of people want to write, something will be written. One of them is going to somehow push his way in. I don't know which one, and you don't know which one. So write your program in a way that you don't care which one gets in there. And then there's the one that would do an exception. In other words, I'm allowing a number of processors to write in the same location as long as they're trying to write the same thing. But if they're not trying to write the same thing, then I'm not going to allow it. So let me give you an example where this exception thing in a CRCW would work. So suppose we have the following problem. Uh, we are given n numbers. Um, Not given, but we have n numbers in memory. We have an array of n numbers, and given x, find out if x is in the array. So if you do this thing serially, your time is going to be O of n. These numbers are not sorted, so you have to go through and check. But suppose you have n processors. So if we have, okay, let's write this down. So serially, O of n. If we have n processors, so every processor is going to be responsible for one of the numbers in the array. So I tell them all the input is in certain location. They go and they read the input, and they compare it to the number x. And anyone who sees that the number is equal to x is going to then output yes to a certain location. So we start out, so our algorithm is going to be the following. Um, every processor, okay, um, initialize output location to 0. Every processor compares its number to x, those that match output 1 to the output location. Now, in a CRCW, whether it's an exception, whether it's random, and whether it's a priority, it doesn't matter. Even the weakest of them, the exception one, since only those who are equal to x are going to output 1, everybody's going to try to write 1 simultaneously, so that's what's going to be written. And so at the end of the program, you check if output location is 1, then x is in the array. So although the time was O of n in the serial algorithm, the time is O of 1 in a CRCW. Any one of them. So in O of 1 time, you can figure it out if you have n processors. Okay, so now we come up. This actually leads us to, I'm giving you a little introduction about parallelism. We're not really going to do parallelism, but so that you'll understand where this other idea is coming from. Although recently they're coming back to parallelism. I see a lot of people in various systemy and practical areas going back to parallel algorithms. So it's not a bad idea to know these concepts. All right, so, but what does it mean? There now is something else that's involved, because whereas in a serial algorithm, we looked at time, the running time, the asymptotic running time of the algorithm as a function of the input length. Now we have another thing playing. We have a function of the number of processors. What happens if I have some problem and if I throw in n squared processors? I can do it in time O1, O of 1, but serially I can really do it also in time O of n. So they came up with the concept of the work. So work of a parallel algorithm is the time times the number of processors, where t is the time and n is the number of processors. So it makes sense that that you would consider that the work, because in some sense that's the energy that you're spending. I mean, all these processors are all working. So if you count the electricity is going to be T times N. It's not going to be, but on the other hand, the whole idea with parallel processing is that your time is going to be faster. So when is a parallel algorithm wonderful? When are we extremely pleased? When are we happy beyond belief? When T times N is equal to the serial time. So if the work of a parallel algorithm equals the time of the serial algorithm, then we say that we have optimal speedup. Now, why is it optimal speedup? I mean, maybe the work is going to be less than the time of a serial algorithm. So why do I say that the optimal speedup that I can have, like the best speedup, is when the work is equal to the serial time? Why couldn't I have the work that's better than the serial time? Because then the serial time is not the best you have. Because think about it. If your work is better than the serial time, then run your algorithm, run your parallel algorithm serially. Don't run every processor together, but run what the first one does and the second one, or in a round robin. One instruction here, one here, one here, one here, one here. Then go back in round robin. Your time is then going to be your work. So your work can't be better than your best serial time, because then you have a better serial time. So whenever you prove a lower bound on a problem serially, then that's a lower bound on the work. You can't have a better work no matter how. It could be that you're going to get even better time, but you're going to lose by adding more processors. You're not going to end up having a work equals time. Work equals time, it's called optimal speedup. So this example that I just gave you, in fact, is an optimal speedup algorithm, because we have n processors, the time is 1, and we answered our problem. The best serial time to answer it is O of n, and so we have optimal speedup. So that's an optimal speedup algorithm. Yeah. No, no, no. It's order. It's equal within order. We're talking asymptotics. Equal. Okay. Let's say asymptotically equals the time. Yes, it's a good point. All right. So, but what about EREW? Suppose we want to solve that problem, but in an EREW model, not in a CREW model. How can we do that? I mean, at this point, we're not allowed anymore to write simultaneously, so we can only write one at a time. Okay, so one way of doing it, and you'll notice that the way of doing it is not optimal speedup anymore, but I'm showing it because it leads to the pattern matching algorithm that we're going to do next. So one way of doing it is going to, so in an EREW, to solve this problem, and supposing that we have n processors, so here's what we're going to do. That's the array. And every one of the n processors is going to obviously check whether it's equal to x. And that they can all check because they're now only checking. Each one is checking his number. So he reads his number, checks if it's equal to x. And then he knows if he wants to output a 1 or a 0. So each one knows if he has a 1 or a 0. So what do we do now? N over 2 of these processors are going to, each one of them, look at a pair. And if the pair has a 1, it is going to compute a 1. And if the pair doesn't have a 1, it's going to say a 0. And then we're going to do the same thing. N over 4 processors are going to do the same thing here, etc. And at the end, the very top, if we have a 1, then x is in the array. And if we don't have a 1, then x is not in the array. So what's the time of this algorithm? We still have n processors, but the time is log n, because this is a complete binary tree. You're taking the pairs and then the pairs of pairs and pairs of pairs. It's a complete binary tree. So the work is O of n log n. The time is O of log n. So we still gain time because we're not doing it in time n. And log n is really, really different from n. So we gain time, but we don't have optimal speed up. So in the 80s, people spent a lot of time trying to understand these different models and um, and showing when you have optimal speed up and when not, and proving lower bounds on optimal speed ups, and all kinds of things like that. So this is the context in which we are now going to look at the next algorithm, because the next algorithm, what it does is it wants to find some sort of a local way or a local algorithm or a local property in which I can do pattern matching efficiently without, but that would lend itself to parallelism. So as we saw, um, uh, the idea of parallelism was important in the past, and it's becoming important again now. But the algorithms that we saw until now, the KMP and the wave algorithm, are all inherently serial because we need what we saw before in order to decide on what we're going to do afterwards. So what we want is a method that uses local kinds of matches. Now, the example that we saw before of the EREW exemplifies an idea that is going to be the idea used by Karp, Miller, Rosenberg in the renaming algorithm. And as you saw, by the way, it's an idea that happened in EREW many times. When you want to do something in logarithmic time, do something in a tree where you work on the bottom level and then you condense pairs of solutions. You have a level above that, you condense pair of solutions, and you have a level above that, and you keep going on until the head of the pyramid. It adds a logarithmic time, but it's parallelizable because you're really doing everything locally, completely locally. In the case of the finding the x, so our work was n log n, which means that if you did it serially, there's nothing to stop you from actually writing an algorithm, a serial algorithm on one CPU that compares every pair of elements, and if both of them are one, and if any of them is one, you pass it on up. And passing it on up just means you write it down in an n/2 size array, then you take and compare every pair and write it in a n/4 size array, et cetera, up until the end, and then you find out if your number is there. So this idea actually can be used in a serial way. So what we're going to do now is we're going to see the renaming idea, and that is more or less the idea that they're doing. They want to do comparisons locally and then bubble them up, and they will get a logarithmic slowdown. So it's not really serially an algorithm that runs in time O of n. It runs in time O of n log m. However, it does allow to parallelize because, as you will see, it's completely local. So what's the idea? So the paper is a paper by Karp, Miller, and Rosenberg from 1972. Karp is Richard Karp, known because of the famous Karp paper of the first dozen or so NP complete problems that he published in 1972 also. But in that year, also came out the paper on the renaming idea. And the idea is simple. You're going to take pairs of symbol, and every pair you're going to consistently rename in a new name. Oops. Now you're going to do this renaming both in the pattern and in the text, so that you're going to, at every level, just rename things, and at the very end, any text location that has the same name as the pattern is going to be an occurrence of the pattern. So let's see how this is done. So how are we going to rename the pattern? So our pattern is P1 through PM, and So we're going to have log levels. So P0, the basic level, is going to be the pattern itself. And the names in P0, every name is the symbol name. But now let's look at pairs of these symbols. So we have P1 and P2. That is a pair. P3 and P4, that's a pair. P2i minus 1 and 2i is a pair. PM minus 1 PM is a pair. Let's take every one of these pairs. There are m over 2 such pairs. Let's take every one of them and rename. But rename in a consistent way, in the sense that if P1, P2 is equal to PM minus 1 PM, they'll get the same name. So since we're talking here about m over 2 pairs, then we'll have the names would be the numbers 1 through m over 2. At best, I mean, if the pairs end up all being the same, then you'll have one name. I mean, if the pattern was A, then the pairs are going to be 1, 1, 1, 1, 1, 1, 1. But you're going to have a shorter pattern now. You'll have a pattern of 1, 1, 1, but its length is m over 2. So we create a new pattern, we call it P1, and it's half the size of the original pattern. At this point, we're in level 2. So we want to go to level 3. We're going to rename all the elements in, well, that was level 1. We'll take all the elements in level 1, we'll take their pairs and rename them, and we get P2, and etc., we go up. So when we get to level I, so we take all the pairs in I minus 1, and we rename them, and we get the level I. So after log m iterations, we're going to get a single number, and the pattern is going to be reduced to the symbol 1. Now, you'll say to yourself, well, how does that help me, the symbol 1? So the question is, what are we going to do in the text? Okay, before we go to the text, let's see how long does it take us to do all of this renaming. Well, so consider this. While you would think that because we have log levels, our time is going to be m log m, but it's not really. The time is linear. Why is the time linear? Because what are you doing here? You're taking m elements and you're reducing them to m over 2. Then you're taking m over 2 and reducing it to m over 4. So what you get is the sum of m over 2 to the I, which is equal to O of m. Because it's m times the sum of 1 over 2 to the I, and that sum actually converges. So even though it seems like we're doing log m operations, we're really working a linear amount of time. Okay, so yes. Yes. The alphabet is going to be between 1 and m over 2. So those are the elements. But the question is, so how do I do that? Okay, it's true that I have m elements and I end up with only m over 2, but you're saying, can I really introduce that in linear time? Which is a valid question. So think about it. In some sense, if you're going to take m elements and you group them into pairs, now you have these pairs. So you have, so far, grouping them into pairs is O of m. Okay, that's linear, not a problem. But now, if you want to find out what name to give, so you give the first pair a name. If you're going to run through all the pairs to see which one of them is equal to the first, then obviously your time is going to be quadratic, because you take the first number, you run O of m, and if no one was there, then the second number you run m minus 1, m minus 2. So the sum of I, where I goes from 1 to n, is n times n plus 1 over 2. which is O of n squared. So clearly, you're right in saying that we don't want to do that. We don't want to do it that way. But we can do it in a different way. So we have these pairs. You can radix sort them because the pairs themselves are, the numbers are going to be between 1 and m. So you want to radix sort. You can radix sort it, the pairs, in linear time. So at that point, just go from the beginning, and when you see a change, you give it. So the first pair gets number 1, and as long as that pair is still there because it's sorted, as long as you're still in the first pair, you give 1, 1, 1, 1, 1. Once you see something else, that will be a 2. And as long as it's the same, you give it the number 2, and you go to 3. So because these numbers are between 1 and m, 1 and m over 2, 1 and m over 4, you can do a radix sort. Radix sort is linear. Okay? So it was a good point, but everyone should rest comfortably. So we have O of m time to get the second level, O of m over 2 time to get the next level. So this is the sum that we get. That's the time. So in fact, it's all written here. The total pattern preprocessing time is the sum where I goes from 0 to log m over 2 to the I, which is O of m. Okay, but now we're going to go to the text. Now we would like to do a similar thing, to do a similar renaming. We go to the text. We'll take the pairs and the pairs of pairs, etc., etc. The problem is this. You have a shift problem. Because if you start in a location of the text where there actually is a pattern location, and you pair, you're going to end up with the same number as in the pattern. But what happens if you didn't? What happens if the text location started somewhere in the middle of a pattern? And so, okay, is the problem clear? What did we do here? So what did we do with the pattern? We said here was the pattern. We take the pairs, we give them names. Then we take the pairs of pairs, we give them names, and the pairs of pairs, etc. Now, here is the text. If the pattern starts in this position, I, and I take these pairs, and I give them the same names that I gave the level 0 in the pattern, then I take the pairs of pairs, and I give them the same names as I did here. And the pairs of pairs of pairs, and I give them the same name. At the end, in this position I, I'm going to have the number of the pattern. And if these pairs didn't have the same numbers, then I wouldn't have the number of the pattern. Because that's how I get this number. So this is all very good. If I started the text, if I started giving the pair numbers exactly at the location where the pattern started. But how do I know where the pattern starts? That's what I don't know. That's what I need to find out. So we do the same thing, but we do it for every location. So although in the pattern, the time, the space is O of m, is linear, in the text we're going to lose. Because what we're going to do is, for every I in the text, we're going to take the pairs and give them a name. So these two get a name, and these two get a name, all of them. But for I plus 1, we're going to take this pair. So we're going to have 2 times, we're going to have 2 of these guys. Different pairs for I and different pairs for I plus 1. And for I plus 4, we're going to have even different ones. Because in short, every position I assumes that that's where the pattern starts, and therefore it does all the pairs and all the quarters and all the 8, etc. So what does it mean now? It means that every one of the text locations actually has log n levels, log m levels that it works on, So already the time and the space is going to be O of n log m. All right. So we do lose the log m, but as I said, at this point, look, it is completely local because uh, you can have processors dealing with the pairs, and they don't care about anything else. Then you have other processors dealing with the pairs of pairs, and they don't care about anyone else. So in log n time, you actually matched the pattern to the text. You didn't need time. You didn't need linear time. You did it in log m time. But the work is n log m. Yes. Well, you do this with n processors. Or if you want to do it with n log n processors, you can also do it. But n processors is enough. Yes, because, okay, so here's what the processors are going to do. Every point in the text, has a processor taking care of it. This processor is going to look to the right, take the element that's there, and name it. Okay, and build the pair anyway. So this processor I is going to build this pair. The processor whose job is I plus 1 is going to look at this pair. And the processor whose job is I plus 2 is going to look at the pair I plus 2, I plus 3. So these processors are going to build these pairs. So they're going to do all of that simultaneously. Then they're going to need to do a sorting. So parallel sort, like I said, I'm not getting into parallel algorithms, so I'm not going to show you a parallel sorting algorithm, but then they're going to do this radix sort. And then once they parallel sorted, which they can do also in log time, they can then do the renaming in constant time at this point. So it's going to take them log squared steps according to this naive way of doing it. There actually are better implementations for parallel algorithms. In fact, there are optimal speedup algorithms for pattern matching. So there really are, and this one can also be adapted to optimal speedup, but they have all kinds of tricks of their own. Because at the time with the PRAM algorithms, they had all kinds of tricks where they say, okay, let's actually not do it using n processors, but let's kind of do it using n over log n processors, and then fix things afterwards in parallel. They had all kinds of techniques, which I'm not going into because we're not doing parallelism. We're doing pattern matching. So as far as pattern matching is concerned, the only thing that we care about here is what is called the renaming technique. Because what it says is take a pair and rename it. So look at it as a serial algorithm. You're taking every pair and you're renaming. Serially, on the pattern, you did the pre-processing in time O of m. And you did the renaming. Now, let's see how serially we're going to do it on the text. So we have log m steps, and at step j, here is the serial algorithm. I goes from 1 to n, and you take these two elements from j minus 1, from level j minus 1, and the elements are the one that was in I and the one that was in I plus 2 to the j minus 1. And in a minute, you'll see why they need to be far from each other, because at every level, your name is farther and farther. The name in level 0, in P0, is from two elements that are right next to each other. But already in the next step, you're taking the name that was, I think I have an example, so we'll see the example. So you're taking the name that was in location I. That name was I and I plus 1. You have to take that together with the name that was in location I plus 2, which was I plus 2, I plus 3. So already for the next level, you don't take the names that are adjacent, but rather the names that are 2 apart. And for the next level, you need to take the names that are 4 apart. So this actually is the formula of what are the names that you take. So you take the text of that level in I, and in level j minus 1, the one that was in I plus 2 to the j minus 1, you take the two of them, and you create a pair out of those, and then you rename them. And you give them either the name of the pair, if they're a pair that is in pj, then you give them the same name. And if it's not a pair that's in pj, then you say bad. So the name you give them is bad, so it's not going to match anything. If you end up at the end with bad, then that's not a 1, so you're not going to have a match with your pattern. So after step log m, there's an occurrence of p in location I of the text if t I of log m is equal to 1. Okay, good. So we have an example here, so we'll be able to work out the details. All right. So this is our text, and this is our pattern. And these are the text positions. So as far as the pattern renaming, because it's BA, BC, we take BA and we take BC. These are the two pairs. And since we have two pairs, their names are going to be, the name of this pair is going to be 1. The name of this pair is going to be 2. And the pattern here is small, so the next level, which is the last one, it's the log 4 level. The pair 1, 2 is going to get the name 1. So that's the pattern renaming. And this is simple and straightforward. Okay? But as far as the text, now we're going to reduce the... Okay. Okay, so we keep this up in order to be able to see what's in P1 and what's in P2. And the text, I need the text itself, so make it smaller. Although at this point you probably can't read this, right? So the text was A, B, A, B, A, B, A, B, C, C, A, B, A, B, C, A. Now the red lines here are the places where the pattern occurred. So the first step is going to say, let's take the pairs. So we have the pair AB, but unlike the pattern where the next pair is going to be AB, in the text, because we don't know where the pattern starts, so the next pair is really going to be BA. So we have the pair AB, and then the pair BA, and then the pair AB again, then the pair BA again, AB, BA, AB, BC, CC, CA, AB, BA, AB, BC, and CA. So we actually write down all the pairs, not just next to each other, concatenated, but rather all the pairs. So in the new text is still of length n, because you still have n pairs. Okay? Good. But we now need to give these guys names. So what name am I going to give to the pair AB? Well, the pair AB doesn't exist with the pattern, so it gets the name B. It's bad. So the first pair is bad. The second pair, BA, exists, and it's a 1. Then we have AB again, which doesn't exist, so it gets bad. Then we have BA. BA is a 1. AB is bad. BA is a 1. AB is bad. BC. Okay, BC, we have a name for it. That's a 2. So we write 2 for BC. CC is bad. CA is bad. AB is bad. But BA is a 1. AB is bad. BC is a 2. And CA is bad. So T1 is still of length n, but this is the alphabet of T1. Okay, so now we go to level 2. And notice that in level 2, That's the last level, in fact, for the pattern. So 1, 2 is the only one that gets the number 1. Any pair other than 1, 2 is supposed to be bad. So let's see what happens here. So since we know that any pair other than 1, 2 is bad, so let's see. Well, okay. The pair B, so we're not going to name B and 1. Why? Because remember, B is this pair, 1 is this pair, and this pair is half of this, is like the half of this and this. So in fact, the two pairs that we need to combine are 2 apart. So we combine these two. But B and B is obviously B. 1 and 1 is another pair. Then we get B and B, 1 and 1, B and B, 1 and 2, B and B, 2 and B, etc. So these are all the pairs that we get from here, and these pairs are 1 apart. I am happy to explain this again. No, is it clear now? Because I have a colleague, Professor Bill Gassarch. He teaches at the University of Maryland. And he has, so he's not, like I told you yesterday, that the ethics of the fathers say that a strict person, too strict, you can't be a good teacher. Well, I think he's a good teacher, but he's very strict. And he's capable of hearing a question from a student and say, what? You ask this and you call yourself a graduate student in computer science? I don't even know what you're doing here. So this is one of the things that he's liable to say. But he also says something else. And I keep telling him that he shouldn't talk like that, but it doesn't help. And then he also does something else. When people ask like someone next to them because they didn't understand something, so he walks over to them, towers over them, and says, the teacher knows more than your neighbor. So if you don't understand something, ask the teacher. So this is something that he likes to do. Now, all this is known. I mean, people who know Bill Gassarch, they know these foibles of his. So, but one day he was giving a talk at Harvard, and in the crowd were sitting Steve Cook and Leonid Levin. Now, Steve Cook, you probably know. He's the guy who proved that satisfiability is NP complete, and that was the first NP complete problem we knew about, which afterwards Karp wrote the famous paper with his reductions, and that led to what the end isn't known yet. But Leonid Levin actually proved in Russia, independently of Steve Cook, that a tiling problem is NP complete. So he actually reduced Turing machines to a tiling problem and proved that it's NP complete. Because he was at the Soviet Union at the time, there wasn't any connection with the United States. He didn't know that Cook at the same time proved it in America. Cook didn't know that at the same time Levin proved it in the Soviet Union. Then, with perestroika and all of the coming out, all the thawing out of relationship, and then the fall of the Soviet Union, but Leonid Levin moved to the US. And so now everybody knew that both of them simultaneously showed that there is an NP complete problem. And so at least, I don't know if here, but at least in Israel now, we don't call it Cook's theorem, we call it the Cook-Levin theorem. But Bill Gassarch was giving his talk at Harvard. The talk had to do with NP completeness, or with the theory of NP completeness. And Cook and Levin were sitting at the end of the class. And then they were talking to each other. So Bill Gassarch walks over to them and towers over them. And everybody says, oh, is he going to be an idiot and say the teacher knows more than your neighbor? Why don't you ask the teacher? But instead he says, the teacher knows a lot less than your neighbor. Oops. And he walks back and continues his talk. So that's as far as that is concerned. But what we can learn from this entire story, other than fun facts about famous people, which is more a gossip column kind of thing, but what we can learn is what I said from the beginning. if something I say is unclear, and especially after 2 hours of teaching, it may be, then I don't I don't mind being stopped. So you can ask me. But if you already got your answer, then that's good. So to get back to this, so because these pairs actually came, they go over each other. So when we want to do the next pair, we have to skip over one. If we had another level, then the next pair that we would take is this and this. So because we would have 2 and 2, so we would take this and this. All right. So these are the pairs, and we're going to have to rename them according to the pattern names. Now, as we saw in the pattern, the only name now is 1 and 2 get named to 1. So the pair 1, 2 gets named to 1, which means that we now need to go through these pairs, and everything is bad except for 1, 2. When we see 1, 2, we're going to name it a 1. We see 1, 2, we're going to name it a 1. And everything else is bad. So it turns out that in location 6 of the text and in location 12, we have a 1. That's the name of this location in the renaming. But that name is also the name of the pattern. If you go back up to the text, you see that in position 6, we had the pattern, and in position 12. So these are the positions where we have a 1 in the renaming step. So we did our pattern matching. Now, the algorithm is, oops, what happened? Yes. The algorithm is simple, and it's local. That's the importance of this. But in fact, renaming has also other uses and not just in parallelism. Renaming also has uses in dynamic pattern matching. Because suppose that you are introducing changes in your text and in your text. So does that mean that next time we're going to need to go through the entire text? So I made one single change in the text, or one here, one there, and then I made another one. Does that mean that I need to go through the entire text all over to do my pattern matching? And the answer is that with renaming techniques, and they have more complex renaming techniques than this one. But with renaming, so obviously your change is not going to affect the names on the sides. It's only going to affect the names in your area. So in some sense, renaming helps also dynamic pattern matching. So we may look at dynamic pattern matching later on, although I suspect not. However, the technique of renaming is the one that we just saw. So let's see now what's the time for text scanning. If we're going to take every pair x, y of the text whenever we are at a level and do some sort of a binary search to find out if this pair xy is one of the pattern pairs, so I can give it that name, then I can do that in log n times, which means that in every iteration we're going to work n log m, and since there are log m iterations, our time is n log squared m. And if the naive way of actually writing a parallel algorithm for this is going to, in log squared time, be able to, n processors in log squared n times are going to be able to do pattern matching. As I said, in fact, there are optimal speedup algorithms for pattern matching. But that's besides the point. Right now, we see an easy way of writing a parallel algorithm, which it's not O of 1, and it's not O of log n, and it's not optimal speedup, but in log squared m time, which is very fast, we can still do pattern matching, and that's good. We couldn't do that, or we had no easy way of parallelizing the previous algorithms because they were all inherently serial. However, if we're looking just for a serial algorithm, the Karp-Miller-Rosenberg algorithm can actually be done serially in time O of n log m, because again, we're going to just use radix sorting, but we're going to radix sort the text pairs with the pattern pairs. And then every time you have a pattern pair, you're okay. So let's look at how it is. We're going to start with the alphabet of 1 through m, and we convert the text alphabet to 1m to b. Now, for every one of the log m steps, we're going to radix sort both the text and the pattern pairs. So the time is going to be n plus m to radix sort them. And when you radix sort the text and the pattern is going to actually give you the names of the next step. The text is just going to now be radix sort. So if you merge them, which you can merge in linear time, n plus m, you can always see whenever you merge a pattern, as long as the text is equal, the text element that comes after it is equal to the pattern pair, you give it a name. And once it's different, it's not going to get that name until you hit the next pattern element. So the time that you actually work on every level is going to be linear, and so O of n for every step. And since you have log m steps, your total time for the algorithm is n log m. So this ends the Karp-Miller-Rosenberg algorithm. Now, at this point, I'm getting to the FFT, but are there some people who didn't come today and want to hear the FFT? Because if that's the case, then we'll call it a day now, and tomorrow we'll do the FFT, which will be long anyway. So we'll do. There are some people who want to see. Okay, so since the next step that we want to talk about is the FFT, and the FFT is going to be the technique that we use for non-transitive relations. So what I'm going to do is introduce a non-transitive relation, show why, because of the fact that it's not transitive, show why the dueling algorithm doesn't work, why the KMP algorithm doesn't work, and then show how we can use the fast Fourier transform to actually make it work. So that's what we're going to see tomorrow morning.